This original WSRE presentation is made possible by viewers like you. Thank you.
What has seemed like science fiction is now becoming reality. We talk robots with research scientist Dr. Jerry Pratt on this edition of Conversations. Dr. Jerry Pratt's fascination with robots began at an early age. He wasn't some kid reading science fiction. He was a young scientist with a knack for inventing. A high school project was so impressive, it landed him a scholarship to MIT, where he would go on to receive his PhD. These days, Pratt is a senior research scientist at the Institute for Human and Machine Cognition in Pensacola, Florida. He and his team have garnered much praise and success for their work in the field of robotics. Recently, they finished second in the DARPA Robotics Challenge. DARPA is Defense Advanced Research Projects Agency, a part of the United States Department of Defense. Dr. Pratt is a 2015 inductee into the Florida Inventors Hall of Fame, where he will reside with historic figures like Henry Ford and Thomas Edison. Several years ago, Dr. Pratt and his wife, Dr. Megan Pratt, launched Pensacola Mess Hall. It's math, engineering, science, and stuff for kids. We welcome Dr. Jerry Pratt to this edition of Conversations. Thank you for joining us.
Thanks for having me.
Your interest in robots began at a very young age. Tell me more.
Yeah, well, I've always been interested in electronics and, like a lot of kids, taking things apart. During 4-H, I had made a couple kind of robots from kits and put those in the county fair, and, they always did well. And, I was always just interested in learning more, so there was this company that used to exist, I don't know if they still do, called Heathkit, where you could buy kits like a radio or whatever and solder it up yourself, put it together, and they had a nice series of electronics classes you could take. So I ended up went through all of them that they had, learned microprocessors, and they didn't really have they had one robotics course, but it was to build a robot arm. But it was really expensive. So I remember, I think I was about a junior in high school, I had written the company letter saying, I don't have a lot of money, could I borrow it or whatever? and they had one that had been open for some reason, and they sent it to me, so I put that together. So yeah, I've always been intrigued with it.
Now, what was the project that landed you the scholarship at MIT?
Well, so there was the National Science Teachers Association used to have, it's kind of changed over the years, I don't know if they still have it, a thing called Design a Duracell Device competition. It was a scholarship competition with just one rule. You make anything you want, it just had to use Duracell batteries. Okay. Right? Because Duracell was sponsoring it, they were paying for the scholarships. Right. So I brainstormed and came up with the knockout keyless door lock. It was something I kind of always wanted. I had a tree fort when I was young, and I always thought it'd be cool if you could enter it by just knocking, da 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 da, and the door opened. Right. So I made that. It had a little microprocessor on it, and you had to program it up, and then you'd knock something, it would record how many knocks you had, the timing in between it. And then you left and came back, and to open the door, you had to knock the same thing to get in.
Wow. Now, do you still have that?
Yeah, I've got, the little prototype. I don't think it works anymore. It'd be cool to make a modern version. Today, with the things available to kids, somebody could probably make that in a couple of days, where it took me about, a few months to put it together back then.
Interesting. So that sets you off on your career. You go to MIT, and what do you start off majoring in?
Well, I majored in mechanical engineering to start, and then since I'm interested in both mechanics and electronics, I then double majored mechanical engineering and computer science. So that took about 4 years. During that, one nice thing at MIT is undergrads have a really good opportunity to work in research in labs. They call it the UROP, Undergraduate Research Opportunities Program. So over a couple of summers, I worked in a couple of labs doing things like making some of the first network interface cards, because this was when the internet was starting, and that was one of my projects. Another one was making a motion tracking system for a autonomous helicopter that was learning how to fly around. So those were the two projects I did undergrad. And then I liked MIT a lot, so I applied to do my master's degree there and got in, and then went through PhD. So that was 10 years total. I was there. I love Boston. It's a great city.
Yeah, it is. You started your own business, right? Or a co-founder?
Yeah, right after getting my PhD, a couple guys in a lab and myself started a company. We wanted to do research, and the mistake we made was not focusing on a product that could make money. We're like, well, we want to have fun, right. and it's not a good way to make money. Right. But we stayed alive for a while. After a while, I was involved with it in about 2 years before I decided, I want to get back heavy into research.
Right. What did you, at the company, what did you invent?
Well, we made a few different things. We built a new robot arm for another professor at MIT. We built exoskeleton, one of the world's first exoskeletons that could add strength and endurance to a human. It was just a knee. You'd strap it on, and it would sense what you're doing and then augment your muscle. So I could strap on a backpack with 150 pounds on it and do one-legged knee bends without getting tired.
Really? Yeah. Interesting. Now, is that still out there in some form?
Well, it's kind of just a research project. We published it, and but that sort of field has really been blossoming now. There's probably 100 groups throughout the world doing exoskeletons. We continue to do some exoskeletons at IHMC, where we have one that allows paralyzed individuals to walk. So far, they can walk on flat ground and use crutches to help balance. And the exoskeleton, you put it on, and it drives your hips and your knees so that you can walk around. What we want to do next with that is get these individuals to be able to, hike through a wooded area, maybe, kind of do paths up a mountain, not, that sort of thing.
Right. For the novice out there who doesn't understand the inner workings, how does something like that work? What's behind it all?
Well, there's various levels. So physically, what it has is a couple motors, one located near your knee, one located at your hip, and the newest version we're adding one at the ankle, and then kind of a structure that matches your legs. And then it really depends on the software you write for it for what it does. So in the simplest form, what you do is once the user indicates somehow that they want to walk, then it just kind of moves the person's legs through some pattern to get them to walk. And that's really all you need in order to get a paralyzed individual to walk again. They typically have really good sense of balance, good upper body strength, so they can shift their upper body and use their crutches to do the balance. What we really would like to get to, and where it starts getting really hard, is where you have the device balanced for the person so that they don't have to use their crutches, or can just kind of lean forward and just starts walking, and if they slip or something, it'll recover. And that's a much harder problem, and and that's related to the bipedal walking, which we do with humanoid robots. So kind of the two go together.
Now, when you said when the person indicates that they want to start walking, how do they go about indicating?
Well, there's a lot of different ways you could do it. One is, and there's a few products on the market now that you can actually buy now. A couple companies that have them. One way, common way, is to lean forward. Another way that we've investigated or have talked about a lot of different ways. One you could imagine is kind of shrug your shoulder if you want to have more control over which leg's swinging. And some devices will have buttons on the crutches you're holding, or even a little thing where you kind of say, okay, I want to start walking on your arm. So there's a lot of different ways, and it's a real interesting area to work in, because the sky's the limit on the number of different ways you can try to get user intent from a human.
Interesting. Is the robotics field, and I guess for lack of a better term, I'll just use for example, Moore's Law, and is that concept starting to work into the robotics field?
In some ways, in that computers are getting faster.
Right.
So a lot of the stuff you look at what our robots can do, to be facetious about it, you could just say, well, it's only doing that better because the computers have gotten faster. And there's a lot of truth to that. A lot of the algorithms we use now are just computationally intensive. We couldn't have used them 10 years ago. But there are a lot of advances in the mechanics and in the control algorithms, but it's not exploding the same way that computation is exploding. Our robots aren't getting 2 times as good every 18 months. Okay. Probably about twice as good every decade.
Okay, about every decade.
But that's still exponential growth, right?
Yeah, absolutely. Absolutely. Well, tell me about, let me get you first to explain to the audience what DARPA is, and then tell me about the competition that you were in.
Yeah, so DARPA is the Defense Advanced Research Projects Agency. It's one of the biggest funders of research in the United States. So there's the National Science Foundation, DARPA, Office of Naval Research, National Institute of Health, and then a few other government agencies. But a lot of money for research comes through DARPA. The DARPA Robotics Challenge was a big competition. So DARPA had done competitions in the past on self-driving cars. A while back, the first DARPA Grand Challenge was to just drive a car have an autonomous car drive through the desert in California. And the first year, none of the cars made it to the finish line, so then they decided to do it again. And the next year, a lot did, and the technology just really advanced a large part due to that contest. So they decided to do that a few years ago with robotics, and at about the time they're developing the competition, the Fukushima nuclear incident happened, where there's a tsunami in Japan that flooded the nuclear reactor, and no one could, we still can't send people into the most radiated parts of it. And had people been able to get in and close a few valves and do a few other things, it might not have been as bad of a disaster. Okay. There was some efforts early on to get some robots that had tracks and wheels into the facility, but things that are designed for humans or that have gone through a natural disaster have rubble everywhere, and these robots just couldn't get to the places they needed to get to. So the competition was kind of modeled after that. They said, okay, what would a robot have to be able to do in order to have been useful back then? And so they came up with, in the end, there was 8 different tasks. So one was driving a car and getting out of the car, going through a door, and then turning a valve. So here you see the video of a robot turning a valve. This is sped up by about a factor of 8. The robots are still kind of slow, and we had a total of an hour to do all of the tasks. A human can probably do all of the tasks in about 3 to 5 minutes. So we're still pretty slow, but we're getting there. Then it had to cut a hole out of a wall picking up a drill and cut a hole out of a piece of sheetrock. Now there's an operator behind the scenes, but the operator's in another building far removed from the robot. Okay. And there's some communication delays, so it's not purely teleoperated. There's a lot of autonomy going on here, but it's not a fully autonomous system. The human's doing a lot of the perception work, but things like the balance is fully autonomous. And here it had to grab a plug and plug it into a different socket. And then there is some tilted cinder blocks kind of simulating some debris in this. And then after that, a pretty steep flight of stairs. So the way the competition was, this was in Pomona, California, just outside of Los Angeles last month. And there were 23 different teams from around the world. We ended up coming in second. First place was a Korean team from KAIST, which is a research university in Korea. And there were probably, like it's kind of like a sporting event. And like any sporting event, if you only have like one competition, just about anybody can win. Right. And there's a lot of really good teams. So of the 23 teams, I'd say about probably around 10 to 16 of them were capable of winning it all. So we performed really well, and we had some lucky things. First day we were unlucky, so we fell down on those cinder blocks that you saw, and then also on the steps. So you get 2 runs, one on the first day and one on the second day. But then the second day we came back and were able to do the whole thing. There was only 3 teams that ended up doing all 8 tasks, and we had the second fastest time. So.
Okay. Now, will they have another one next year?
No, so this project's over now. It's it was a really big DARPA project, but there's other things that come in the pipeline now. NASA is talking about doing a space robotics challenge that'll be similar, but focused on Mars exploration rather than a disaster recovery. And then some other countries are thinking about doing their own sort of competition and making it international.
So as you bring this robot back to Florida, will you continue to improve on that concept? How does that?
Yeah, we're going to keep working on the robot. So by the way, the robot's called Atlas. It's from a company called Boston Dynamics in Boston. They just were purchased by Google last year. But it's a real nice robot. So we didn't do the hardware for this one. We've, for our exoskeletons, we do the hardware. For some of our running robots, we do the hardware. But for this one, we're one of the software teams. There were 6 different teams that use the Atlas robot, and then there's 7, sorry, and then the other 16 teams had their own robot. But yeah, we'll be getting the robot. Well, we have the robot back now, and it's all set up, and we're going to continue the research. So that DARPA funding has ended, but we have some funding through NASA to show how we could use robots for space exploration. And so we're going to continue working on that robot, and we're also working on a robot called Valkyrie that NASA Johnson Space Center has made. It's also a humanoid robot, and so we'll work with them on that. So we've had some really good hardware. I mean, I've been working on this stuff for 20 years, and I've had some okay robots in the past, but these 2 we're working on are really good. So there's probably a good 5 to 10 years of research we can get out of these 2 platforms.
I want to show some other video that we have. The one your robot that was, I guess, ran about 30 to 40 miles per hour.
Yeah.
Now, what type of robot is that?
Okay, so this is called the Hex Runner. It's first blush it looks like a wheel. Okay, we have to launch it from this pendulum thing because it's not stable at under 20 miles an hour. The fastest speed we got was 33 miles per hour. We think we could get this one a little bit faster, but but 33 is top speed we've got here. It looks like a wheel, but it's really a running robot. It's got legs, and it's got a flight phase where the robot's in the air. Sometimes it doesn't, where both feet are on the ground, but sometimes it does have flight phase. And it's storing energy in each leg like a running animal does, and releasing energy. So it's just that it's not swinging its legs. Each leg comes over the top. So it's a spokeless wheel, but it runs. And it's self-stabilizing, which means there isn't any feedback control. Typically when you have a robot, you have like a lot of sensors that are feeding back like the orientation, and then you're making a lot of small corrections with the motors really quickly, like 1,000 times a second. Here there's no computer. All there is 2 motors, one that's just spinning the legs and one that's being used for steering, and that's it. And so what this robot has shown is that fast running is mostly open loop stable, we call it, where there's, where you don't require a lot of this feedback. And with animals, like it's kind of, we've been trying to model some simulations and robots on ostriches. And when they're running as fast as they can, there's just not enough time for sensors to detect what's going on, work its way through the nervous system, have some decision be made, and go back to the muscles. The time it takes for that to happen is about the same amount of time as a leg's on the ground. So the animal can only be thinking, if it's reacting several steps ahead. It's not reacting right now, which is typically what we do for other robots like Atlas. So we want to show that that there doesn't have to be really quick feedback. And so with that Hex Runner, even though it doesn't look like an ostrich, if you look at what's happening with the ground reaction forces, they're very similar to what's happening to the ground reaction forces with ostrich. And we believe the stabilizing mechanism, so as it starts falling over and what makes it recover, we believe it's very similar to how an ostrich works. So we have a series of robots we want to make. That's the first one. And we've simulated some of the other ones that start reciprocating the legs instead of having them go over the top, and then have them, instead of having just a straight pogo stick-like leg, have an articulated leg like an ostrich. So we have a really nice simulation that shows this, that kind of looks like an ostrich, and again, there's no feedback. There's just and another nice thing about it is there's, in our models, there's just one big motor per leg, instead of having like a lot of motors on each part. And then there's an intricate system of pulleys and springs, and kind of like what you'd see in an animal, where there's tendons that behave like springs and some muscles that cross multiple joints. So that's what we're trying to reproduce in a robot.
How would that be used in the practical world?
Well, it's more of a research project right now. It's trying to generate the knowledge. In the future, if you, for whatever reason, you need a running robot and need it to be efficient, so that instead of, you know, batteries lasting 10 minutes, you get, you know, 4 to 8 hours out of it. You need to be much more efficient. Robots today are just notoriously inefficient, the legged robots. Like Atlas, with full battery pack, gets about an hour and a half of operation before it's done. Whereas like a human, as long as a human has enough water, I've heard stories that you can walk almost across the country without eating. You know, you'd be in bad shape by the end.
Right.
But a robot, you know, you've got a couple hours only.
Interesting. As you look out in the future, where would you see robotics in the next, you know, 15 to 20 years?
You know, that's hard to say. The big economic application is going to be in houses eventually, right? That's where all the money is for any product, is you got to get to the Joe public. And what people always seem to want are, you know, robots that can do your chores, can, you know, fold your laundry, can put your dishes in your dishwasher, things like that. You know, these things are still super expensive, so we really need to get the prices down. Before that, robots like the ones in DARPA Robotics Challenge would be useful for places where you need a human presence, but it's too dangerous or expensive or whatever to get humans there. Now, there's not a lot of applications for that, you know, disaster, space exploration. So it's, you know, there's the military applications. So it's hard to say. You know, I don't know if you'll see robots everywhere in 15 years. I think you're going to see exoskeletons all over the place, whether factories or just paralyzed individuals walking down the street, or you know, medical applications. And you know, eventually you'll be able to, you know, suppose you're getting up in age and want to go hiking with your grandchild. You know, you'd be able to just rent at a sports store or something that you just, you know, strap on your knee and be able to keep up with your grandchild while hiking. So I think the technology is far enough along that if people find the commercial applications, it'll happen. With things like bipedal walking robots, the technology still needs probably another 5 to 10 years before there'll be commercial payoffs, even if there are potential commercial markets.
Very, very fascinating. Very, very fascinating. You and your wife started an organization to kind of bring science in with to children, to kids, called the Mess Hall.
Yep.
What is it?
So the Pensacola Mess Hall is kind of a play on words in two ways. So MESS stands for Math, Engineering, Science, and Stuff. It's kind of a rearrangement of STEM, you know, science, technology, and engineering and math. But you know, Pensacola is a Navy town, and the Mess Hall is a Navy cafeteria. So the Mess Hall, it's a science museum that's very hands-on. We try to make sure that just about every exhibit or everything we have in there is something where you actually get to touch the materials, do things with it, rather than a lot of typical science museums where you just push a button and so this is Darth Vader during the 501st, which is a group that likes to dress up in Star Wars costumes. They'll come once a year, and so we'll do Watto's shop where you can do take apart. So we just, from the landfill, we'll get you know, a lot of the old electronics people bring in, and we'll just set it up on a table, let kids take it apart. And, you know, you always hear about kids always want to take apart stuff when you're young, like myself, but you don't want kids taking apart all your stuff at home. So this is a place where you can do that. So we'll do that occasionally. We'll have a lot of local scientists come in and give demonstrations. You know, we do have a lot of typical science exhibits like this one where you kind of, you know, just push the button and see the cool phenomena. But that's, you know, we have a few of those. What we try to do is have everything be hands-on. And this is called a harmonograph. It's a little machine that has a bunch of pendulums in the bottom that draw a really cool figure. So when we were starting the Mess Hall, we've been talking about doing this for about 10 years. And, you know, almost as soon as we got to Pensacola. But it was really daunting because the typical science museum has about 100 exhibits. And Megan was, you know, saying, you know, this is going to be really hard to do. Like, okay, give me 3 exhibits, I'll show you that we can build them. So she gave me the harmonograph and a couple others. I over the course of about 3 or 4 months, I went ahead and built them in our garage. I love to kid around with my children and say, well, you know, we're going to have this science museum here, and, you know, we'll have the gift store over here in that corner of the garage. I'm like, Dad, there's not enough space. Like, yeah, it'll work out. This is wind tubes where you just have a fan blowing wind up, and kids can make parachutes or whatnot. And some kids will spend 2 to 4 hours playing with a single exhibit. And that's why hands-on, you know, is so important. Is it really engages the kids and makes them interested. Absolutely. But we are short on space, and the place we're in now, we started one summer right off of Palafox Street in a place that was only about 2,500, 3,000 square feet of useful space. And you know, that's not enough room to have 100 good exhibits, right? So Megan came up with this great idea of having what's called mess kits. So again, play on words. You know, mess kit is the box of food you get. So I got one here.
Got one here, okay.
All right. So, you know, so this is a Chinese food box, right? And everything at the mess hall is kind of food based. We've got, you know, straws and you know, just everything you'd find in a food store. And but what comes in a mess kit is, instead of a bunch of food, it's kind of what you need to do a science kit in a box. So it'd be a little instruction book that kind of, you know, walks the kids through it step by step on what to do. And then there'll be challenges and like how's it all work in the back. And then a bunch of simple materials that, you know, things you could do at home usually. But what's really annoying when you get like a science book that says, oh, you can do this at home, all you need is these simple materials, is finding those simple materials in your home. Here it's all right there, you can't fail, right? It's so this is balancing pencil, which is one of these phenomena that I loved when I was a kid. Let me just do it up really quick here. So you got your
about 2 minutes
pencil. All right. So you just put a bunch of weights on the bottom. And we, you know, like to give kids like things they can, you know, make it pretty, even though that's not part of what's important for what's going on here. And if you do it right here, you kind of balance your pencil.
Oh, awesome.
Yeah, and so it kind of, you know, we don't know if the kid learns the science concept here. The science concept is, if you have your center of mass below your pivot point, then it's stable, because if it goes that way, it comes back and whatnot. And actually this has a lot to do with why bipedal walking robots work, but I won't get into that right now. But it allows a kid to really kind of think that they've kind of discovered it on their own, right? It's kind of, you know, a lot of times a kid will do something different with the kit that's somewhat obvious or whatever, and think, hey, look what I discovered. It's like,
great.
Yeah, so it's...
Jerry, I'm out of time. I wish I had more. What a pleasure spending time with you. Best of luck to you.
Thanks.
Thank you so very much. By the way, you can keep up with Dr. Pratt's work and all of the scientists over at the Institute for Human and Machine Cognition at ihmc.us. Dr. Pratt and his wife, Dr. Megan Pratt, are bringing science to kids through Pensacola Mess Hall that we just talked about, and you can learn more about that at pensacolaMessHall.org. And by the way, you can see more of our conversations online at wsre.org/conversations, also on YouTube and Facebook. I'm Jeff Weeks. Thank you so very much for watching. I hope you enjoyed the broadcast. Take wonderful care of yourself, and we'll see you soon.
Support for this program is provided in part by these corporate sponsors. And by viewers like you.